Hello everyone, you're welcome to today's class. Today we're going to be considering a topic under physics titled Fundamental and Derived Units. So first of all, I'm going to start by explaining what a fundamental unit is. Now, when you talk about fundamental unit, what is fundamental unit? Now, fundamental unit or fundamental quantities first before the unit. Now, fundamental quantities are the basic quantities that are independent of others. So they are the basic quantities that are independent of others. So underline that word, independent. They are independent of others and cannot be defined in terms of other quantities or derived from them. So it cannot be defined in terms of other quantities or derived from them. So move further to explain what fundamental units. What I just explained is fundamental quantities. Now, what is fundamental units? Now, the fundamental units are basic units upon which other units depend. So other units are being gotten from these fundamental units. So they are the basic units upon which other units depends. Now, I have a table that that's my table 1, which I'm going to be, which is written on the board. My table 1 here contains fundamental quantities and their units. Now, so these are examples of some fundamental quantities alongside their units. Now, I have 7 fundamental quantities and their units are all here. They are SI units. And the meaning of this SI, it means System International. That's the meaning of SI. So they are the acceptable units all over the world that are being used in terms of measurement. So that's it. So let's proceed. We have the quantities, the SI unit, then the symbol of the unit. Now, my first fundamental quantity here is length. So any measurement of length, example, I want to measure the distance from my house to my school, I want to measure the distance of a football field and everything, is all called, they are all classified under measurement of length. Now, so the SI unit for length is meters, while the symbol for the unit is M, that's meters. So the next is time. Now, if I'm taking measurement maybe of a particular interval, maybe an event, I want to know how long an event lasts. Now, that's all those, they are all classified under measurement of time. Now, the SI unit for time is seconds, and the symbol for the unit is S. Then the next one is mass. Mass. So mass is measured in, the SI unit for mass is kilogram, and the symbol of the unit is kg. While we have electric current, the SI unit for electric current is ampere, and the unit is capital A. Then here the symbol, the SI unit is ampere and the symbol is capital A. Then I have temperature. Temperature is measured in Kelvin. That's the SI unit for temperature, Kelvin. Then the symbol is K, capital K. Then I have amount of a substance, which is measured in moles. That's the unit is moles, and the symbol is mole. Then I have luminous intensity. So luminous intensity is measured, the SI unit for luminous intensity is candela, which is given as CD. So all these 7, they are all what you call fundamental quantities, and these are their units that are called fundamental units. So moving from fundamental quantities, now we are going to what you call derived units. Now, when you hear the word derived, that means something is gotten from something. Now, in the case of derived unit is simply the combination of 2 or more fundamental units. So when you combine 2 or more fundamental units to give you a particular unit, that unit is called a derived unit. Example are all stated on the table above on the board. So here I have my table now. So this is my table of derived quantities and the units. Now, so this is my derived quantity. I have area. Now, derived quantity, my derivation, and my derived unit. So I have area. Now, area is simply length times breadth. So you see, the length is a measurement and the breadth is measurement of length also. So here I have the unit of length is meters, while the unit of breadth is meters. So meters times meters, I'm going to have meters squared. So that's the unit of area. I move to the next one, which is my volume. Now, my volume is length times breadth times height. Now, the unit of length is meters, the unit of breadth is meters, and the unit of height also is meters. So meters times meters times meters, I'm going to have meter cube. Now, The next one is density. So density is simply mass over volume. So my mass is measured in kilogram, while my volume is measured in meter cube. So now kilogram divided by meter cube, I'll have kilogram per meter cube. So the next one here is my velocity. Now my velocity is given as displacement over time. So my unit of displacement is meters, while my unit of time is seconds. So I have it as meter per seconds. Now the next one I move to is acceleration. So acceleration is given as change in velocity with time. That's over time. So I have change in velocity divided by time. So my velocity, change in velocity, is given as meter per seconds. That's my change in velocity, meter per seconds. Now divide by time again, which is in seconds. That's why I have meter per second square. So they are all derived units. Now I have force. For my force is given as mass times acceleration. Mass is measured in kilogram. Acceleration is measured in meter per second square. So I have it as kilogram meter per second square. Now this is it. Instead of you writing this lengthy unit, maybe after calculation, writing the lengthy unit, the scientists came up with an idea. Okay, why not we get a collective names for all these units? So they're able to get a collective name for force, for the unit of force. Now instead of kilogram meter per second square, the collective name for the unit of force is Newton. And Newton is denoted using capital N here. So the next one is energy or work. So energy or work, the symbol for energy or work is W. So energy or work is given as force times distance. Now, so force is in Newton, while distance is in meter. So my unit of energy becomes Newton meter. Force Newton, distance meter, so I have a Newton meter, or the collective name for the unit is given as joules, which is noted using capital J. So that's it. So the next one is power. So power is simply work over time. Now, so my work is given in joules, while my time is in seconds. So I have it as joules per second, or the collective name for the unit of power is watt, which is noted using capital W. I move to pressure. Pressure is simply force over area. Now, my force is given as in Newton, while my area is given as meter square. So I'll have Newton divided by meter square. My unit becomes Newton meter square. That is Newton per meter square. Or the collective name is given as Pascal, which is denoted using PA. That's capital P and small letter A. Then the last one is momentum. Now, so for my momentum, I have momentum to be mass times velocity. So my mass is measured in kilogram. My velocity is measured in meter per seconds. Or I can say my momentum is also Newton per seconds, because in Newton I have kilogram per meter per second square, then multiplied by seconds. So if I multiply it, I will end up having it to be equal to kilogram meter per second, same as this. Because according to law of indices, this S here is raised to the power of 1. So minus 2 plus 1, I'll have it as minus 1. So I'll have the same thing as this. So it's either you denote it using kilogram meter per seconds, or you use Newton per seconds. So that's all concerning derived units. Now, there are some prefixes that are associated with all these units. Example, you see the distance of a particular place is being given in kilometers. Now, so that kilo that is attached to meters, because the unit of distance is meters. So now the kilo attached to the meters is a prefix now that change the meaning entirely. Now, if you have meter, example, I have 1 meter. Now, me introducing 1 kilometer, it means I'm introducing 10 raised to the power of 3 of that same meters. Now, so that's it. So these are some basic prefixes as stated here on this table that are associated with units. Now, so the first prefix that is associated with unit, there are more, but I'm taking it from here. Now, the first prefix here on the table is giga. Now, giga is denoted with capital G, and giga is equivalent to 10 raised to the power of 9. That's giga. Then the next one is mega. Now, mega is denoted using capital M, and mega is given as 10 raised to the power of 6. That's mega. Same as going down to the next one, which is kilo. Now, kilo is denoted using capital K, and kilo is equivalent to 10 raised to the power of 3. Hecto is denoted with small h, and hecto is given as 10 raised to the power of 2. Then I have what we call deca. So deca is denoted with small d and small a. That's small letter d and small letter a. And deca is denoted using is given as 10 raised to the power of 1. Then the next one is deci. So deci is denoted using small letter d and is given as 10 raised to the power of minus 1. Then I move down to the next one, which is centi. So centi is denoted using c, as in centimeter and the rest. So denoted using small c and is given as 10 raised to the power of minus 2. The next one is milli. Now, milli is denoted using small letter m and is given as 10 raised to the power of minus 3. Then micro. Now, micro is denoted with mu. That's the name of this symbol, mu. So it's denoted with mu and is given as 10 raised to the power of minus 6. Then nano. Nano is denoted with n, as in nanoparticles and the rest, or nanofarads, nanometers, like that. Nanogram, like that. So nano here is denoted using small n and is given as 10 raised to the power of minus 9. Then the next one is pico. Pico is denoted using small p and is given as 10 raised to the power of minus 12. Then the last one is femto. Here, femto is denoted using small f and is given as 10 raised to the power of minus 15. So that's all on the prefixes that are associated with units. So thank you very much for joining us in today's class. I hope to see you in our next class. Bye.